Hello everyone and welcome again to the second lecture of your short series Vibration with MATLAB. In our previous class, we have seen the response of a single degree of freedom undamped system under the free vibration condition. In this lecture, we are going to study the response under the influence of a harmonic excitation. So this is my single degree of freedom system which has been represented by a spring and the mass. I am assuming that the mass is only able to move only in this vertical direction. Therefore, the system is having 1 degree of freedom and I am applying a harmonic force on mass, and the magnitude of my harmonic force is F naught sine omega t, where F naught representing the amplitude of the excitation force, and this sine omega t is making it as a harmonic function, and omega is the excitation frequency in radians per second. So before we talk about the MATLAB coding of this force vibration case, let's understand some theoretical aspect of the harmonic excitation condition. So one important thing under the harmonic excitation we must understand is the resonating condition. So what happens if we will see the equation of motion of this single degree of freedom system under the harmonic excitation? My equation will be mx double dot plus kx is equal to f naught sine omega t. So this is my excitation frequency, and if I will find the natural frequency, it will be under root k by m. So in case of resonance, my excitation frequency become close to the natural frequency, and at this state the amplitude become very high, and the situation is known as the resonating condition. Similarly, when we are having excitation over the system, what is your general expectation? Do you think the output oscillation will be governed by the excitation frequency, or it will remain with the natural frequency? For example, the natural frequency of my system is, let's, 5 hertz, and I am giving one excitation of magnitude of frequency 8 hertz. So what is your expectation, whether the system is going to oscillate with 5 hertz or it will oscillate with the 8 hertz frequency? Please understand that this is an undamped system. So particularly for the undamped case, the output will not only govern by one of the frequency, instead of that both the frequency will come together in our system. For example, here I am showing two plots. Let's, the force is 0, that means this is my system and this is the force excitation. But suppose that F naught is 0, that means I am doing just free vibration and I have given some initial displacement. I am not talking about what is the initial disturbance. I am just showing here that this is the response for the free vibration case, where the time period will be governed by the natural frequency. Here omega n, I am showing it in radian per second, so my time period will be 2 pi by omega n. If I have an excitation and the excitation frequency is omega f now, do you think that the output will be purely governed by the excitation frequency? So we can think that now my oscillation will be corresponding to the excitation frequency, and this would be expected output or the response of displacement with respect to time. But since this is an undamped system, there is no damping. What actually happens, the natural part is not going to decay, because when we generally see the conventional force vibration condition, there are two parts. One is the transient phase, another one is the steady state phase. But that is actually there when we are having damping. So what happened, because of the damping, the natural excitation die out with respect to time, and later on we have only excitation because of the external excitation. But in case of undamped system, both frequency will remain in our system, and therefore we will have superposition of the two excitation. So here I am showing that these two frequency will come together in your system, and then instead of observing either of the frequency, there will be a superposed condition, and the response will look like in this way. So this is our expectation from our MATLAB code, and the output will be the combination of two frequencies. So when we will make our MATLAB code, this will be one of the check that the response should not be governed by only one frequency. However, if your excitation frequency will become close to the natural frequency, we expect that both the frequency will be same, so output will have only one dominating frequency and the amplitude will be very high because you are at the resonating condition. So we will see it when we will make our MATLAB code. Now the last part before we go and see the MATLAB code is the state space formation of our governing equation. In the last class we have already seen that how we do the state space formation, and after doing the state space formation your second order ordinary differential equation becomes two single order ordinary differential equation. This is my governing equation, mx double dot plus kx is equal to my external force F, where F is your F naught sine omega excitation frequency into T. So when I will consider that x dot is equal to x1 and x is equal to x2, this is conventional method to convert the given equation through the state space formulation. So this is our second order ordinary differential equation. Now I have these two variables, so I can replace in my governing equation and I will get, if I will do the differentiation of this equation, I will get my x double dot will become x1 dot. Similarly my x dot will become what? X2 dot, and x dot is nothing but your x1, so I can also write it is equal to x1. Let's replace this in the original equation. I will get m x1 dot plus k x2 is equal to my f, and when I will rearrange my term I will get x1 dot is equal to minus k by m x2 plus f by m. This is my first single order ordinary differential equation, and this equation will give output as my velocity. Why? Because I have considered velocity is equal to x1, and this is the equation in terms of x1, so the output will be velocity. Similarly the second equation will directly be this equation, so the second equation will be x2 dot is equal to x1. Now using these two equations, I can apply a simple numerical integration method for solving a single order ordinary differential equation. So the benefit of applying the state space formulation is what? Earlier we have to deal with a second order ordinary differential equation. So the numerical method required to solve this equation will be little complicated. But yes, I am having two single order ordinary differential equation, I can use trapezoidal rule and many more equations. So this is all about your state space formulation, and now let's see your MATLAB code. So what I will follow here, first I will explain the MATLAB code here itself line by line, and then we will move to the MATLAB platform and we will see the response. This is your MATLAB code. So we are having two code, main program where we are calling a function, that is my second program. So here I am also showing my second program. Let's try to understand this line by line. I have written this code for this problem where I am having a single degree of freedom system, stiffness 2000, mass 2 kilogram, and the excitation is 5 sine 2 pi 90. So here the excitation frequency is 9 hertz. If I will calculate the natural frequency of my system, that will be 2000 by 2, which will comes out as 31 approximately, and in hertz I will get my natural frequency 31 by 2 pi, that will comes out around 5 hertz. So here the natural frequency is 5 hertz and the excitation frequency is your 9 hertz. So let's see how the response will look like when I will see my MATLAB code. As we have already seen our previous lecture, the code was similar to the same this code, only few lines I have added here to incorporate the force term. So first three lines are corresponding to just explaining the code, and these three lines are my comment line. CLC and clear all are there to clear the window as well as clear the workspace. Line 6 is the definition. I am defining my mass m is equal to 2, stiffness 2000. Then I am writing input for my excitation. My excitation is f naught sine 2 pi omega ft, where omega underscore f is my excitation frequency in hertz and t is my time vector. Here I am giving input in 9 hertz, so this is my excitation frequency. In 5 is the amplitude of my excitation force, which is 5 given in the question. Then I am defining that these four constants will be global constant, because I have to call a function and in that function I have to use these four constants. So I need to make them global so that I can switch from one function, one program to another program, and I can use the same constants. Then line 12 showing the time step. In the last class we have exclusively discussed that how to decide the time step. So here I am not going in the discussion that how to decide it. I am taking it that 0.005. Line 13 is my definition of my time vector. I am having my time vector from 0 to 2 second with a time step of 0.005. Line 14 is standard line, that is for the input condition and for a given problem, as I am not giving any initial displacement as well as the initial velocity. So here my initial velocity and initial displacement are 0. Line 15 is for your ODE 45 function, that is your MATLAB standard code. So here the T solution and Y solution representing the time output, as well as the Y solution will have your output velocity as well as the displacement. ODE 45, ordinary differential equation 45, this is standard MATLAB function which is already defined by the MATLAB to solve a first order ordinary differential equation. That means I can write my own code, like I can use the trapezoidal rule, that is a numerical integration tool, to solve the first order ordinary differential equation. But here MATLAB has already given us this standard function, so I am directly using ODE 45, and this line 15 is actually standard format which is required for ODE 45. It is already defined by the MATLAB. So after ODE5, I am writing here that the test ODE123, this is a function I have created, because in this function I am writing my situation which I have derived through the state space formulation. Then this is my time input and this is my initial condition. The same we have already seen in our previous lecture. So let's move ahead. Line 16 and line 18 are just plotting of my displacement and the velocity. As here I am calling a function that is test ODE123. So this is the my function where dy is the output of my function. Test 12 ODE123 is the name of this function. Input time and input initial condition. This is the same global function definition of my global constants. Here I am writing in line 4, I am writing my force, that is f naught sine 2 pi and omega ft, and then I am using this in the fifth line. So my fifth line is corresponding to x1 dot, that is minus k by m x2 plus f by m, and my sixth line is corresponding to x2 dot is equal to x1. So I will get an output in terms of velocity from here and in terms of displacement from here. And line 7th I have written because in MATLAB, particularly when we use the ODE function, the output should be in terms of column vector. So here dy1 and dy2 actually creating two rows. So I am doing a transpose. This dash is actually converting my dy vector into transpose. So earlier I was having a row vector, later on it will become a column vector. So this is one line which is required to convert a row vector into a column vector. In today's class we will also try to learn that how to make a good figure file, because whenever you want to write a manuscript, a paper, there you need good quality figure, or if you want to show your output in some PPT, how to improve your output figure file, that we will also learn today when we will see the response. So this is all about your MATLAB code. Now let's move to the MATLAB window and see the response. This is your MATLAB environment. If I will run my code, I have saved my code with the name of single degree of freedom underscore force underscore response underscore ODE solver. And the second one is the function which I am going to use to get the response of this force. So let's run our main code and see the response. So here is your output. We are having two output figure file. Figure 2 is corresponding to your velocity versus time, and figure 1 is corresponding to your displacement versus time. And you can see here we are not having a single harmonic output, as we have already seen that both natural frequency as well as the forcing frequency will come together. There will be a superposition. Therefore we are having this sort of output which is the combination of my 5 hertz and 9 hertz, because when we will see the code here we are showing that this is line corresponding to excitation frequency, and I know the natural frequency is 5 hertz. So I am having my output which is the combination of two frequencies. Suppose I want to change my input and I want to see the resonating condition. In case of resonating condition, my excitation frequency will be close to the natural frequency. So let's make this as 5. Now my natural frequency as well as the excitation frequency are 5 hertz, or they are close to each other. Now see what will be the response of my code. So here you can see that this is your response where the amplitude is continuously growing. It is why, because this is the resonating condition and your amplitude will grow with respect to time and it will reach to infinite condition. So this is also a validation of your code, that when you are making your natural frequency close to the excitation frequency, what happens? Now we are having only one dominating frequency. There is no combination of two frequencies, because in the previous case the wave was not perfectly harmonic wave. There were combination of two frequencies, but here we are having a single frequency, but amplitude is growing with respect to time because it is a resonating condition, and resonance is there in my displacement versus time as well as my velocity versus time. Similarly, if I will have a random input, for example I am having a frequency of 4 hertz, and then let's see that what would be your response. In case of 4 hertz excitation, the output is something like a beating phenomena. What happens in the beating phenomena? You have already studied your beat phenomena in your mechanical vibration as well as in your plus one, where we say that if the two frequency try to come together, or there is a superposition of two frequencies which are close to each other. Let's see that what is your beating phenomena. In case of beating phenomena, if you are having two frequency, let's omega 1 and omega 2, and both are close to each other, so the superposition will have two frequency, which will be omega 1 plus omega 2 by 2 as well as omega 1 omega 2 by 2. So output will have combination of these two frequencies, and it will look like that the amplitude is growing and decreasing. So this is a typical plot for a beating phenomena, where the amplitude is also a function of time, which is increasing and decreasing. At the same time there is oscillation. So there are two frequencies. One is, this is high frequency, another one is the lower frequency, which is the variation in the amplitude. So in similar fashion we are having output here from our MATLAB code, which is showing a beat kind of phenomena. So with these three different output, now I hope that you have understood that how to write a code for the forcing condition and how to see the responses. Now the last thing, as I said, we will also learn that how to make a good figure file. Here I am having two figure file. Let's close one figure file. There are two option to improve the figure file. One, you can directly add or modify your figure file. For example, here I can write the insert. I can give the X label. When I will click the X label, there is a line here, so I can write that this is my time, where I am putting it in seconds. Similarly, I can give input for the Y label, so I will get here that it is my amplitude, as well as I can also give the title to my figure, that this is my displacement versus time plot. In similar way, you can also improve the quality of this line, and for that what you need to do, you have to click this button, that is this arrow button, and then you can click your line here. So this is the line. You have picked the line and right click. When you will see there is a color of line, line style, line width, let's make the line width 2, so the line will become more thicker. At the same time you can also change the color. Then you can also mark some point. For example, you want to show what is the amplitude as well as the time at this point. So for that you have to click this marker and select the marker and click here. So you can see that this is the time. X level is 1.55, that means you are showing it at 1.55 second, and your Y is the amplitude, that is 0.01155, that means this is in meters. Similarly, you can also improve the quality of your figure. If you want to export this figure or you want to show this figure in a PPT, what you can do, you just go to the file and then click the export setup. In the export setup, go to the rendering. In the rendering, you have the resolution in DPI, change it to 600, apply to the figure, and then you can see that now your figure is improved. When you will take a copy of figure or you will save this figure, it will be of higher quality. So all these things you can directly do by taking your figure file, or you can do it with the command line itself. That these three features similarly you can explore in the MATLAB. And what is the trick to get this tool? Either you can Google it, or in the MATLAB you can simply write help and type what is the command, so you will get the detail of that command. When you will do so, you will get all the detail of your plot, what you can do with your plot. So with this note, I am closing this session, and I hope that you have understanding how to write MATLAB code to get the force response of a single degree of freedom system. In my next video, I will solve the same problem using the beta numeric method. For this session, thank you.